Good morning, good afternoon, good evening from which other part of the world you are in. So today is 54th webinar from in our TAIym webinar series, and it's on seismic design of tunnels and underground structures. Today we have with us Dr. Conrad, Dr. Professor Youssef Hashash, and Mr. Wataru Okada, and Dr. Mohsén with us, and they will speak. They are the members of Working Group 9, IT Working Group 9, which is on the seismic designs of tunnels, and quite well-known personalities in the field of seismicity. So introduction is not needed, I guess. And over to you, Conrad.
Thank you, Rushi. I appreciate it. Well, good morning, everyone. We will go ahead and get started. We certainly appreciate the opportunity to present today. As Yoshi said, my name is Conrad Felice, and I am the current animator for the Working Group 9, which is Seismic Effects for the International Tunneling Association. And fortunately, in my project background, I'm very familiar with the issues in India. I've had the pleasure of being the geotechnical engineer and foundation engineer for your Bandra Sea-Link structure in Mumbai, now the Rajiv Gandhi Sea-Link, which is, I think, one of your signature structures within the country. So I very much appreciate being here and leading off this lecture. We've got some very good folks to give you some background on seismic design. I'll give a basic overview and introduction, and then I'll turn it over to Youssef, who will go into some of the details on the seismic design that we're currently applying. And then we've got a project description where these tools have been applied, and then some risk issues that Mohsén will be presenting, and then we'll be available for any questions as well. So to just begin, my outline for at least the introductory talk is basically address some of the worldwide seismicity issues, some of the vulnerabilities that we have, and then go into some specific hazards. And then I'll close by giving you a little bit of background on our working group. The world does have a significant exposure to seismic hazards, as you can see here, and in particular the Indian subcontinent, as well as the region where I practice and live, which is the northwest of the United States. So we do have a significant vulnerability, which is why seismic issues are extremely important in our design practice. Now, if you follow the UN, we've got 195 countries. But within that 195, recently more than 100 have been exposed to earthquakes with magnitudes greater than 5.2. And within our ITA, or International Tunneling Association community, 44 of our 80 member nations are actually on that list of being vulnerable to seismicity. There's been some discussion in the past that tunnels are essentially very good places, and they indeed are when it comes to seismic effects. But we've got historical publications and research that shows, we are subjected to damage and significant damage, particularly when the ground motions are greater than 0.5 g. So we do have that historical perspective, and we continue to accumulate data in our literature. It's not only the acceleration values, it's the depth at which our tunnels are located. And you can see if they're less than 50 meters, we do have significant damage. So it's a distance as well as a ground type, which you can see on the lower graph that it expresses the kind of vulnerability to our geologic settings and our stratigraphy. And these are recorded. We've got a good record in the literature of what the damage has been and what we can expect in terms of acceleration and the kind of structures that have been exposed historically to earthquakes. In terms of the hazards, the first one on top of the list is the intensity of the ground shaking. And whether we're looking at portals or whether we're looking at liner systems, there has been demonstrated damage to significant earthquakes at these structural systems. The next is fault rupture. One of the significant things is fault rupture, and it requires some special design considerations. The image you see on the left shows an actual fault displacement at the Wenchuan earthquake that occurred in 2008. I was on the reconnaissance team there, and that's nearly a 3 to 4 meter disruption of a fault exposure from that earthquake. Even though we have our structures, we do need to pay close attention to the portals in particular. The tunnel is no longer a functioning, viable system if we can't have access to it. So the fact that landsliding can affect portal structures is also very significant and one we need to pay attention to. Another issue, particularly for the more shallow tunnels in the softer ground areas with high groundwater, is liquefaction. The loss of strength due to the ground motions and poor pressure development can indeed cause uplift and significant damage to our structures. So we do need to pay attention to this phenomenon and address it quite carefully in our design practice. Words have been bantered around like sustainability and resiliency, and what you're seeing here is some substantial damage during the Kobe earthquake. And these pictures are courtesy of Antonio Bobbitt at Purdue University, who's worked in Japan extensively. And we do need to pay attention to resiliency because putting these structures back in operation and the minimization of downtime is very significant and one we need to pay very particular attention to. My last slide before I turn it over to Youssef is on our working group. It's structured such that we have a tutor or somebody from the ITA Executive Committee overseeing our working group. I am currently the animateur, and Haitao Yu from Tongji University is my vice animateur. And you can see the scope of our activities over on the left. And we have our meetings in person at the World Tunnel Congresses. We just had one in Stockholm this past year. And next year it will be in Montreal. And if you're planning to attend the working group, the World Tunnel Congress, I would invite you to attend our working group meeting. With that, I will stop sharing and turn it over to Youssef.
Thank you, Conrad, and thank you so much for inviting me to present at this webinar. And first thing in order would be to share my screen and confirm that you can see my screen. Are you able to see my screen?
Yeah, it's visible, Professor Youssef.
Excellent, excellent. Well, once again, thank you so much for inviting me, and I want to acknowledge my current and former PhD students who have helped me in preparing this presentation, which I titled as a framework for seismic design and analysis of underground structures. For those of you who might be familiar with the paper we published in 2001, this would be an update, and this is something that we are working on as we speak of that work, of that paper. So I'll build upon what Conrad has mentioned regarding the seismic performance of underground structures. Then we'll talk about the seismic design framework and the stepwise approach we take from site characterization to seismic hazard and ground motions, preliminary seismic analysis, advanced seismic analyses, and with some concluding remarks. So while, as Conrad mentioned, underground structures generally perform well during earthquakes relative to above ground structures, we still have failures. We still have problems with our underground structures. Conrad mentioned Antonio Bobbitt's photos from Japan. This is a picture of the Daikai subway station that was damaged severely during the 1995 Kobe earthquake. This is the portal that was mentioned by Conrad, happened during the 2008 Wanchuan earthquake in China. You have uplift due to liquefaction. This is in Urasu, Japan. This is also damage to lining in Japan. In Italy, damage to lining, and this is damage to a tunnel during the recent Turkey earthquake, and the collapses that were observed. So tunnels do experience damage during earthquakes, and hence we want to make sure that we are designing for these tunnels appropriately. So the types of damage we have span from lining cracking, concrete spalling, water leakage, portal damage, flotations, permanent shear displacement, especially if when you're crossing a fault. Another type of shear displacement would be due to a landslide that goes across your tunnel, and then a partial or total collapse of a tunnel. And this is a schematic representing, for example, what was observed during the Daikai subway station collapse. So let's go on into our seismic design framework. In our first step, we have to identify what our design approach criteria. Sometimes it's code-based, performance-based, or resilience-based. And this has been evolving, especially over the last 25 years since we wrote our 2001 paper. Now, once you establish the framework, the approach, the criteria that you need to meet, then our work as engineers. First thing we do is site characterization. You do everything you usually do for characterizations that is needed for a geotechnical project, an underground project, and then we add a few more things that are needed for seismic evaluation. You need field investigation, laboratory testing, and also you need to identify and evaluate faults, some that might cross your alignment and others that might induce ground shaking. Then we go to a second stage whereby we define our seismic parameters, controlling seismic parameters. Whereby we do a systematic seismic and fault hazard analysis. In a systematic approach, sometimes we do that deterministically, other times we do it probabilistically, and they're quite complementary. Then we get to the issue of how we select ground motions representative of the hazard that we are interested in. We talk a little bit about basis of motion selection and spectral matching, and then we talk about site effects, meaning where we usually develop ground motions that are representative of an equivalent rock outcrop, and then we have to look at how the ground modifies these ground motions. Then in our evaluation, the first thing we want to do is evaluate whether there is a potential for ground failure, because ground failure imposes significant loading on a tunnel much larger than that of usually a ground motion or a shaking type of evaluation, which is also needed. We also do simplified analysis methods, empirical, analytical, and simplified. We usually do them in a preliminary stage, initial phase. And nowadays, when we're going into detailed design, we have the tools that were really almost inaccessible for us 25 years ago, or were very, very costly, which is 2D and 3D modeling. We have appropriate constitutive models. We can include the structural modeling explicitly instead of simple beams. We also look at the interaction. We'll talk about pseudostatic versus dynamic analysis, but nowadays, performing dynamic analysis is far more accessible and available to us. We'll talk about some special cases, influence of adjacent structures, and even more advanced modeling we can do, where we can do seismic fluid, structure, soil interaction. So in terms of the code-based approaches, usually it's a standard for many projects, but it may not be Site-specific can be overly conservative or under-conservative and has limited flexibility. A performance-based type of approach would look at projects that are not covered by design standards. And in fact, many projects do not have the capabilities. Is there a question?
No, Professor. There was someone mic on. I have switched it off.
Okay, I appreciate it. I just want to make sure if there are any questions. Thank you. The performance-based project approach would be to look at, okay, I don't have something that for which a design standard exists. And what you will find is that many of our underground structures do not have a specific code that is useful and suitable for them. It sets specific objectives for the performance. It requires advanced expertise, can be time-consuming and costly, but that cost has been going down over the years, especially as you bring in teams that are experienced with this. You may need extensive simulations. Again, the cost of these is going down and usually requires an independent peer review process. Now, a risk project is a project whereby you look at not just about your tunnel, but you look at how that tunnel plays a role in the community resilience in the long term. We have to think about our tunnels, our structures, that we don't just design them for 20 years or 50 years and say, okay, we're done. Tunnels live with us for hundreds of years. And so we need to keep that in mind. So we focus on long-term recovery and functionality. One framework for that would be functional recovery. You try to minimize downtime and economic losses. So this is for lifeline structures, but systems that you need to be operational shortly after a major earthquake. It requires a comprehensive planning, engaging the community, can be complex, and it definitely requires an independent peer review. Now, in terms of site characterization, I won't spend too much time, but we have a variety of tools and we need all of them for the characterization of our site. We need to find out where our faults are. We need to know the stiffness and strength characteristics of the soil. We need to do laboratory testing. And a key tool that you need is direct characterization of shear wave velocity profile. In the US, nowadays, coming very, very soon, the new codes will not allow for a conversion from SPT to a shear wave velocity or strength to shear wave velocity, but they will require a direct measure of shear wave velocity. I'm a big proponent of that because there are so many uncertainties associated with these conversions that people have to do. So the tools that are becoming far more accessible and reliable, downhole seismic testing, CPT, seismic cones, for example, as well as suspension loggers are some of the best tools. There are surface techniques, but those also require specific expertise in understanding or characterizing it because they require inversion. Then we get into our seismic hazard analysis, whereby we start with, if we think of the deterministic seismic hazard, you have your site, you have your various sources, you evaluate closest source to distance, you take the maximum events that are going to produce the maximum intensity measure you're interested in, could be peak acceleration, peak spectral acceleration, or any number of factors. And then you say, okay, there it is. I got it. This is what I have to deal with. And so commonly used in early years, but it's useful worst case scenario, can be useful for capping a probabilistic approach, because probabilistic approaches that are not constrained by the physics of the problem would cause problems for us. Now, a deterministic probabilistic seismic hazard analysis follows a very similar approach, but you end up with something like a uniform hazard spectrum. And then there is a tool that will allow us to bridge between deterministic and probabilistic, and that is a type of either conditional mean spectrum or conditional spectrum that is incredibly useful, and it allows for a more refined analysis because the uniform hazard spectrum, depending on your seismic setting, does not really represent any single source and can be overly conservative. And hence, something like a conditional spectrum is extremely useful. And we've used it on many projects. Now, for fault displacement, whereby your tunnel is crossing a fault, we have now advanced procedures to develop and evaluate the fault displacement because that's what you're trying to do. We really cannot accept that our tunnel goes out of service completely if a fault displaces. We are able to now develop designs whereby you can accommodate displacements and regain function of the tunnel fairly quickly. And so, for example, I am in Los Angeles. There's you have tunnels crossing faults all the time, and they design them to accommodate these displacements. And you follow very similar steps to a seismic hazard analysis, but focusing on the fault displacement, and you have both deterministic and probabilistic approaches, and there will be always a lot of opinions about it. There's no single opinion about these, and you try to reconcile a variety of evidence pieces that in developing your estimates of displacements. Then you have ground motions. So now we're looking at the shaking that's resulting from nearby faults, and we have to get our ground motion. We have to have a target spectrum fit our ground motion. There are many issues associated with these. I'm not going to these, but I want you to be aware. The tools that we have had developed enormously for, say, processing these ground motion. This is a processing tools in deep soil, which is now our seismic carried by rock science. And you can look at your ground motion. You look at your spectra, both in terms of response spectrum and Fourier spectrum. And by the way, modern seismic hazard analysis is focused more on response on Fourier spectra, not response spectra, as it gives us a more refined analysis. And the next for the series of seismic hazard development approaches, one of them is NGA West. NGA West 3 is focused extensively on that as well. Now, in terms of site response analysis, why we need it? Because the ground itself modifies our analyses, modified our ground motions. And since we're dealing with a longitudinal structure, we're not looking at just simply the ground motion propagating vertically, but also longitudinally, causing incoherence and push and pull on the tunnel lining. And this is, we can do it in 1D, and this is with deep soil, which is, as I mentioned, is now RS seismic. And also you have three-dimensional approaches. This is thanks to Dr. Ellison from Europe, where he uses LS-DYNA to do a 3D site response analysis. My research group is also doing some 3D site response analysis, and we are you can stay tuned to look at some publications coming up with this. Now, in terms of ground failure that we are interested in, we have to look at fault displacements, which we just spoke about. Liquefaction, you have to look at the effect of liquefaction and how that would impact your tunnel. And as I showed you earlier, you may have seismic slope instability. For example, during the Chi-Chi earthquake in Taiwan, a lot of damage to tunnels happened because of slope instability. So you need to understand these impacts as well. Now, in terms of let's look at how to evaluate the response of tunnel to shaking. There are simplified SSI approaches. I always recommend that you start with these, and these would give you an initial estimate of your shaking. You simplify a lot about the ground, about the tunnels themselves. They give you a first order estimate, and you need that to see whether you are going to see a problem and also decide how to develop advanced analyses. You need to know about the ground behavior. You have to do your free field analysis, the analytical approaches, simplified approaches, and pseudostatic approaches. Now, one approach that people know a lot about, which is the Mononobe Okabe, or the dynamic earth approach. We have to remember the origin of these. Goes back over a century ago and is designed for retaining structures that move. Can be used usually for short structures whereby the PGA is less than 0.4 G. But once you deal with real structures, you can underestimate or overestimate the earth pressures. And so you don't want to deal with that. You need to be very careful. And some people still rely on it, and I do not recommend it unless there are some very, very good reasons to do that. Now, there's a free field deformation approach whereby you assume the tunnel moves with the ground, and there is also another solution whereby you assume a perforated ground. But that means that you have to think of it this way, is that the mass you've removed, its equivalent shear stiffness is equal to that of the lining the ground, what you've substituted. It may be okay in some soft ground situations, but in these ones you have large strains, nonlinearity may be not that good. There are some simplified closed form solutions and then some pseudostatic approaches that we have that can be very helpful, again, as an initial estimate and for simple structures that you may be dealing with. So in terms of thinking about this, is you start with 1D site response analysis. You have 1D or a seismic. There are other tools. I highly recommend deep soil or seismic because of the totality of the analysis approaches if you're looking at 1D. Now, if you go for 2D or 3D, you want to have more advanced tools. In 3D analysis, I have found it with my group that currently LS-DYNA gives you some of the fastest calculation times, and so therefore you're able to conduct very complex analyses. We can look at tunnels separately, tunnels by them also separately, but now we can look at the interaction of tunnels and buildings. Why? Because that interaction is important. Or buried reservoirs. We find that the sloshing of water in buried reservoirs is important. And we can then we can show the shortcomings of the simplified approaches and what you learn from the advanced approaches. Now, to develop these 2D models and 3D models, that requires advanced expertise and training. And so that is something that is important that your engineers have if this is what you plan to do. And you would have to properly represent the soil behavior with all its hysteretic response, the structure itself, and we have to look at whether you have a reinforced concrete, steel, the columns, the connections, the shear development, and all the nuances of the structural detailing can be incorporated in modern models. And now we can do things whereby I can represent a full building and a tunnel and the interaction between these. So this is something we could not have even contemplated 25 years ago when I published the 2001 paper, but we've published recently papers on these where we can actually represent this. And you can have 3D motions and incorporate the complexity of the underground structures and the tunnels themselves. So this is something we do. And by the way, we're doing it for real projects. This is not just research. This is for real projects. As I mentioned, there are a variety of tools that are available for you here that for various packages. Whatever package you use, need to be very careful about the modeling and do some checking. You can always check the results versus closed form solutions versus analytical approximations, and then, of course, extend it beyond that. And you have to have the elements, the structural elements, the material models, the soil structure interface. That's very important, especially if you're looking at force transmissions. So you're here dealing with mesh density, the representation, the material constitutive behavior, the interface, and the interface condition is very important. The base conditions, is it rigid, elastic half space? And if you want to know more about that, you need to look at RS Seismic/deep soil for that, and then the boundary conditions for that. The pseudostatic approach is useful, and we needed it at a time whereby dynamic analysis whereby we fully trace the nonlinearity were rather expensive. And so this is an analysis we have done in 2010, whereby we looked at the effect of different boxes. And we did two types of analyses. One is pseudostatic analyses. These are the open symbols. And then we did dynamic analysis to show the difference between dynamic response, a true dynamic response, and approximation of pseudostatic. And you can see that, well, for the racking ratio, for example, for a double box, you are going to underestimate the racking ratio. For a single box in a stiff soil, you are going to potentially slightly overestimate. Now, here in this range, whereby you have soft soils, you can be underestimating, you can be overestimating relative to the dynamic analysis. Well, and also here we also look at the impact of temporary walls and whether we ignore them, which is often the case, or we fully represent them. And we found actually not representing them can underestimate the demand on the final structures. So it's not always, shall we say, conservative to ignore temporary structures. What all the work we have done, bodywork says, is that for your specific structure, you do want to do site-specific dynamic soil structure and interaction analysis, because you do not really know whether you're overestimating or underestimating it. And again, nowadays, this has become more accessible. So now I'm going to give you an example of a series of projects that we have conducted to look at the effect, in this particular case, tall buildings on underground structures. So this is the problem we have. This is a tall building, and it's during construction and also as part of the permanent structure. Now, we know that a building will have a base shear. Well, that base shear doesn't stop at the property boundary. It has to go somewhere. And therefore, if you have an adjacent, very nearby subway tunnel, well, that load is going to go into your subway tunnels. And so we have conducted a systematic study as part of a PhD work inspired by real-world problem using multiple different height buildings. And we looked at 2 and 3-dimensional ground motions. And we started looking at the impact of a variety of factors. For example, the depth of the foundations, the relative location to a tunnel. Now, when you look at all of these factors, you find the racking displacement change are dependent on these factors, and hence you do want to represent them. The dynamic thrust is impacted by the intensity of the ground motion and by the structure you are dealing with. So there are all these variables that are in place. We did sort of try to fit some curves to them, but there's really no substitute for conducting simulations that are specific to your projects. Because also, don't forget that the building footprint is limited while the tunnel is a longitudinal structure. So this is some of the summaries of the key behaviors we've observed. We find that we looked at ground motion parameters, number of stories, height of basement, pile length, tunnel depth, tunnel building the building distance, VS30 soil stiffness. We found, for example, PGVP ground velocity has a strong correlation. We have, for example, the pile length, there's limited change, but tunnel depth, there's an increase in racking displacement, and dynamic thrust is increased for mid-rise and decrease for high-rise building. It all depends on the rigidity of the foundation and the depth of those foundations. So here's another example whereby we conducted a 3-dimensional analysis of a buried structure. Let me explain what these buried reservoirs, think of them, they have the shape of a pizza box, and they have a lot of columns to support the roof, and they are buried underground. And then you cover them with soil, often to protect the water, but also to reclaim the surface for, say, sports facility, community sports facilities. Now, up till recently, people have simulated these as 2-dimensional. Have they experienced damage? Yes, they have. For example, the Balboa Reservoir in the 71 for San Fernando earthquake. So now what we have is these reservoirs have water in them. And we know that during an earthquake, water can slosh. So that will apply dynamic pressures on the sides. But also, if the water is too high, it can hit the roof, and that could cause damage to the roof. So we need to represent it. Now, here you're looking at it in 2D. So we have to have now water, structure, and soil interaction. So we're having to look at all of those together. And we were inspired by some underground reservoirs in Seattle and in Los Angeles. And we developed a series of centrifuge tests that we conducted at UC Davis to develop some experimental data on these, and these were heavily instrumented. And then we calibrated our models. With these measurements, we calibrated our models with these centrifuge experiments, and then we conducted our simulations for these. And with our simulations, we could not fail these reservoirs in the centrifuge because we were afraid of causing damage and having pieces fly around when the centrifuge is spinning. But in our simulations, we were able to take our structure all the way to collapse and see the collapse modes. And we can see how, here you're looking at the surface collapse. And what were our key findings is that the response is truly three-dimensional, and the forces go from each side of the supporting walls to the corner that lead to potential significant damage. Depending on the columns and how you design them, you can collapse them. And so therefore, you have to design these columns properly. We have a diaphragm effect. So it's not a pure underground whereby we talk about pure displacements, but it is actually a true soil structure interaction whereby also the inertia of the roof is playing a role in the performance of this very shallow underground structure. Okay, now that takes me to my concluding remarks. The possibility of damage collapse of tunnels can be reduced by considering a systematic seismic design framework. Seismic design objectives, including functional recovery considerations, need to be defined. Representation of the seismic risk hazard is needed in order to perform a successful seismic design. Simplified approaches to analyze the seismic response of underground structures provide a good first approximations, but are limited by the simplifying assumptions. Advanced analyses are now with us. This is our time. And they can help us tackle these and better represent structures. And I'm happy to also talk to you about the role of Gen AI in this space as well. I showed you examples of the importance of soil structure interaction, tall buildings, better reservoirs. We have advanced analysis through software, computing hardware, big management tools, generative AI, by the way, that can help us nowadays with these. And so we're able to do these. And with that, I think I am done. These are some useful papers and books on the topic. And I think, while I may say, we'll reserve questions to the end of our various presentation. And with that, thank you so much.
Thank you, Professor. I think now we have Mr. Okada with us. Hello. Mr. Okada,
Wataru, you want to unmute? Okay.
Okay, yeah, just sharing my screen. Okay. Okay, sorry, just trying to present the right screen. Sorry. Right. Can everyone see my screen?
Yes, your screen
This
is
is
visible.
presentation slide. All right. Okay. Here we go. Okay. So my name is Wataru Okada. I'm also a member of our ITA Working Group 9. So today I'm going to present a case study of seismic design of CRL tunnel. Now, CRL, short for City Rail-Link Tunnel, is a recent project we completed in New Zealand. Now, I'm going to start the presentation by talking briefly about the project overview, and this will be followed by some key aspects of the seismic design of the rail tunnel for the project. Now, the project is located in Auckland, which is in North Island. It's the largest city in New Zealand, and it's a new underground rail scheme which connects CBD to an existing rail line on the city fringe. It's practically complete. We're just in the testing and commissioning phase, so the project is expected to be open sometime next year. Right. Okay. So in terms of the scope of tunneling work, the biggest component is obviously the running tunnel. So it's a 1.7 meter twin tube, internal diameter 6.24, and we also have two new stations shown in green, and we are redeveloping two existing stations as well. In the middle of the scheme, we have a new station. It's 30 meter deep. It's in the hard rock. So instead of doing conventional sort of open cut construction, we decided to do a mined platform tunnel station. And at the southern end of the scheme, we have mined caverns instead of TAIym tunnel. And in between two running tunnel, we have 4 cross passages connecting the running tunnels. Now, so the project is being delivered by Link Alliance under Alliance procurement model. So we share profits and risks and pain gain sharing model. So in the Alliance, we have 3 international contractors, and we have 3 design firms. And of course, we have City Rail-Link as the owner participant. We work closely with 2 sponsor organizations who are the ultimate asset owners. Right. So let's just look at each tunnel component. Now, the biggest, longest one is the running tunnel. They are bore tunnel constructed using a TBM and lined with a precast segmental lining. As I mentioned, 6.24 diameter. There are 3 types of segmental precast segments. So type A1, which is roughly 80 to 90% of the tunnel, is steel fiber reinforced, and the remaining then 20% is conventional reinforced concrete with steel cage reinforcement. We have mined cross passages at 4 locations. They are spaced at 200 and 204 meter based on the fire life safety assessment. They provide emergency egress in the event of tunnel fire. And they also house mechanical and electrical equipment such as deluge valves and communication cabinets and so forth. As I mentioned earlier on, we have a mined tunnel station at Karangahape. So what happened is this one platform was constructed before TAIym complete first half of the scheme, and the tunnel breaks in, and the tunnel just walks through, and it's relaunched out the other end and completes the second half of the scheme. And same goes for the downline as well. And it was constructed using road headers. Now we have tapered caverns, mined caverns constructed using road header. Again, the reason we have mined cavern at this southern end of the scheme is because we have rail bifurcation where one track splits into 2 tracks. So we need larger section to accommodate the Y junction. So the largest cavern is called MC 2050, and its largest span is 70 meter and 11 meter high. Now, yeah, so for all the tunnel, the seismic design philosophy is essentially the same. Just if you're wondering, and just in terms of site characterization, we did a program of site investigation and came up with this geological interpretation. So tunnel alignment is predominantly in orange material. It's called East Coast Base Formation Sandstone and Siltstone. We call it EU2, and we have localized sort of lenses and pockets of weakly cemented sandstone at the southern end, and in the K Road Karangahape station, we have moderately stronger sandstone. We call it EU3. So this is a quick summary of the geological units we find for CRL project. So the most predominant material, EU2, is basically interbedded sandstone and siltstone, and its UCS is typically sort of 1 to 5 MPa range, so it's considered probably weak rock, so that has implication on the soil structure interaction as well. At least in New Zealand and Australia as well, I guess. So existing seismic codes are kind of geared towards the surface structure, such as bridges and buildings and the likes. Now, so they are not quite adequate for underground structure. The key thing to bear in mind is that underground structures are restrained by surrounding medium, so they are not sort of above structure that are governed by sort of inertial effects. Just and a bit of a background is as Conrad briefly touched on, there's some early works that sort of suggested tunnels are a better place to be, but So in the early years, based on our literature review, there wasn't consistent seismic design approach. Yeah, in the international scene, I guess, but we had pretty major earthquakes in the late 80s and 90s, and that seems to be when sort of people sort of really appreciated the importance of seismic design, and from from the 90s onwards, sort of more sort of robust, I guess, the seismic design philosophy started getting published and all that. So in the New Zealand scene, we had a recent development where New Zealand Transport Agency included a sort of peak ground strain approach, such as WAN 1993, as a recommended approach for underground structure design. Now, whereas subsurface structures are sort of predominantly based on force-based approach, so underground structure sort of for our project, we adopted a deformation-based approach. So as I mentioned early on, so the seismic response of an underground structure is dominated by the ground response rather than the inertial property of it, like period and mass and frequency and so forth of the structure itself. So we need to determine the free field deformation and also the seismic parameters as well. And once these I think soil structure interaction and seismic effects are worked out, they are added to other sustained loads and look at each load case for the check the capacity, structural capacity of the tunnel. Okay, so Professor Hashash covered this in very good detail, so I'm not going to go into detail other than to say we started off with a simplistic sort of closed form approach, and that kind of gave us, I guess, preliminary results, and that kind of gave us sort of structural actions and all sorts. Right, and just in terms of our seismic design criteria and parameter, we need to design for 100-year design life. That's what the client requested. And we considered two different earthquake scenarios. So ODE, the tunnel needs to maintain continued operation. So the train need to basically keep running. Whereas maximum design earthquake scenario, MDE, is more focused around public safety and preventing loss of life. Now, another important aspect for seismic design criteria is we need to look at criticality of the tunnel in terms of economic loss, life occupancy, and the post-disaster emergency functions and all that. So taking all that into account, we came up with importance level of 3. And taking all that into account, we designed for 1 in 2,500 year event for MDE and 25-year event for the ODE case. And we have 2 different site classes, but mostly in class B, which is in rock condition. Now, site characterization, So we invested in geophysics testing, and so we did MASW as well as VSWP. So we had direct measurement of shear wave velocity as opposed to sort of a correlation using other types of testing. So it's direct field measurement is always preferred than sort of conversion, as Professor Hashash mentioned early on. And so from that, we obtained shear wave velocity and used it for our seismic design. Now, so we also used numerical modeling and used ground response as an input, and then work out what the structure does, how it responds to the ground deformation. And on the right, you see the resulting plot of bending moment and the axial force, and you see the structural capacity curve. So this is how kind of we look at the structural capacity of the tunnel lining and design the concrete and the reinforcing and so forth. There are a few other considerations, I guess. Yeah. So 1.7 kilometer scheme, we look at, we did the design analysis at 16 location, and we looked at the range of ground conditions, rock cover, overburden, and in some places we have critical surface structure. So it's important to cover the whole range of ground conditions and overburden, etc. Sensitive analysis are quite important given the uncertain nature of input parameters like characterization and of course seismic response, etc. Another thing we need to bear in mind is this is more like a construction aspect as well. Whether it's TBM or mined tunnel, in TBM, like a mine bore tunnel, for example, TBM always overcut. And you build a segmental lining inside the shield. So you always end up with a little bit of annular sort of void around the tunnel. So you have to grout it, and occasionally, every now and then, you somehow end up with a void in grout. So it's important we identify those voids and do secondary grouting. And likewise for mine tunnel, you cast in situ, for example, and you have to check there's no void by doing what we call contact grouting, so that tunnel structures actually restrained and actually act like a locked-in structure. So that it actually behave like we expect in a seismic event. So in conclusion, soil structure interaction is key aspect in tunnel seismic behavior. We adopted a design sort of based on deformation, and I can't emphasize this enough. Good investigation data go a long way to characterize site and also the response characteristic of the ground. Sensitivity analysis are always required to design for uncertainty. So that's the end of my presentation. So I'll just stop sharing here.
Rushi, will you bring on our last speaker for this morning?
Yes. Is he online? Dr. Mohsén is online. Yeah, I can see
Yes.
him. Dr. Mohsén. Oh, okay, yeah.
Yes. Can you hear me well?
Yes, yes. So we can hear you. You can now
Because
share
I
your
right
screen.
now having a bombardment of the messages from this group, and I was also in another conference before lunch, which was run in Turkey. They're also still messaging each other on something. So if there is a sound of blipping, please forgive me. I'm just going to share my presentation right here. Can you see my screen?
Yes, now we can see your screen. Yeah.
Yes. So a little bit background of what I'm going to say. It's there is a very short presentation my side. We have you know, when you are going to design your blast in a field, there are two ways for Swedish industry right now to design your blast. One of them is while you're doing the process, and one of them is to do a design before the process has started to apply for permits. Um, Both of these cases for designing a blast for a long or long-term project, ongoing long-term project, or starting a small project pretty close to the very sensitive infrastructure, are quite important to be able to know how much vibration or the land displacement we are microseismicity, as we can say it, we are going to generate in our project. Uh, but these two things are the vibration and the land displacement. Basically, the microseismicity is heavily affected by the rock property. So what type of rocks we have, and what is the quality of that rock, and what is the rock property. So is it weathered, is not weathered? Is it crystalline? What is the porosity? What is the fluid saturation? This usually to design that, what we call it in industry is a site specification. The site specification is a very important character to make sure that your design is going to work in a granitic rock and also later works in a sedimentary rock if you just tweak it a little bit. This site specification data is usually very complicated, and we try to use AI generative app. I'm not going to use the advertisement part for this presentation, so I'm just going to give you the scientific background of that. We are using the pre-collected vibration and microseismicity data from the former and ongoing project to feed it into our AI generative system in order to calculate and formalize a generative equation that can give us the vibration and the microseismicity in a certain location. What does it mean? That I'm going to use a tunneling data in Stockholm that has happened in 2000 or 2001 and until 2005. And now if there is going to be a new infrastructure building pretty close to a hospital, and they would like to do some blasting to clean up the soil and reach into the fresh rock, I'm going to use those data from the tunneling part to design that how much TNT and explosive material you're going to use, which type of design you have to use it, and eventually how much vibration and microseismicity you are going to induce to a certain location, to the certain distance from your project, which means that how much you're going to affect my hospital or a sports center that is pretty close to your project. So I'm just going to show you one slide. If you can see my cursor, basically we are going to define that this would be the blast area. And then we are going to show that based on the distance that you have from the blast area, You do have a certain important infrastructure pretty close to the blast area, some not, some very important but far away. And then we are showing you that how much vibration that infrastructure is going to receive based on the certain amount of explosive material and a certain design of explosive material, that explosion that you have decided for your project. This is just a fruitful thoughts. This type of equation and this type of calculation is not very nonlinear, so it's pretty linear. And everybody who's listening to this presentation with a little bit of a Python coding would be able to create your own small app to be able to calculate the vibration at a certain distance from the location of the blasting. This is good for the design of the project before you start the project and apply for permits. And also when you are doing the same project, imagine right now, follow with me, follow my thoughts, that if you started the project, imagine that you're in the middle of the tunneling and you're going to do the blast and cut drill tunneling, and then you do have a receivers in a certain point where I'm moving my cursor. If they are actually your receivers, they are your vibrometers. So then by doing this operation continuously, you would be able to cross-correlate the data you get from the analytical calculation and AI feed information, and also from your data collecting in the field. So you would be able to correct your data on the way you go, and then you will have a better and better accuracy. And this is quite important in a large tunneling project, especially when you are talking about the metro tunnels and you're going to crossing a number of important infrastructure on the surface. So that would be quite, right now in Sweden is quite an interesting thing to follow and monitor. And I'm pretty sure that it would be the same case in the countries that you are staying as well. With that, I would like to conclude my presentation. It was a very short 4 or 5 minutes presentation. Thank you for listening, but I'm here to answer questions.
Thank you, Dr. Mohsén. Saurav, are you online?
Yes. I'm
Yeah, please take over.
For those who are new to this topic, it is an honor to express our heartfelt gratitude to our distinguished speakers and to spotlight the pioneers shaping seismic design of tunnels and underground structures. Dr. Conrad-Felice has set industry benchmark through his leadership in geotechnical engineering and major infrastructure projects. Professor Youssef has revolutionized seismic analysis and soil structure interaction with advanced numerical modeling and innovations like deep soil, earning global recognition for his transformative research. Mr. Wataru brings decades of global experience in tunnel seismic resilience, influencing best practices through landmark projects and research. Dr. Mohsén advances rock mechanics and computational modeling, integrating cutting-edge numerical and experimental approaches for seismic tunneling. Their collective expertise continues to inspire innovation, deeper understanding, and resilience in underground infrastructure worldwide. Thank you once again for this session. That said, let's move to Q&A session. I believe most of the questions are answered by Professor in the chat box only. First question is by Manisha Yadav. She's mainly want to know about the uplift for the tunneling. She wanted to know a few practical examples of mitigation measures that have been successfully used to limit seismic uplift. I believe this question is for Professor.
Yes, well, thank you. And I saw there were some additional questions. I thought it'd be easier to discuss them instead of typing them in a little boxes. So yes, for an existing tunnel, I'll give you an actual case history, which I worked on and which inspired my thinking about it, is in the San Francisco Bay Area in the state of California in the United States, there are two fairly old immersed tube tunnels in the 1930s, 40s, and 50s that were placed in trenches. And then there was fill. First, they put a small base of sand underneath them, and then they had fill around them. And as part of a program to understand their seismic response based on recognition of higher hazard that the area would experience relative to that time, it was determined that these fills that were placed, and they were uncontrolled fills in a sense, would be susceptible to liquefaction. And so the question was, what do I do? Can I improve that? The problem is you have to balance. If you try to improve it in a classical way, first you could damage the tunnels, and these are fairly old tunnels. And instead, what it was decided was that you need to mitigate the impact of liquefaction. And the impact would be that the soil, as it liquefies, it'll turn into a fluid and try to push the soil up. And so if we can prevent this further upward movement, then we can eliminate the impact of the liquefaction or limit it. And so what it was decided is to improve ground along sort of parallel to the tunnel, but not underneath the tunnel where the soil will liquefy. And what that would do is will cut off the liquefied soils from going underneath and pushing it. So it was a very smart way of looking at it. I'm not going to claim it was me. I was a junior engineer at the time, and the late Dr. Birger Schmidt, he is the one who first came up with the idea, and I spent many months trying to demonstrate via calculation that it would work. So it really depends on the condition that you are dealing with. And so instead of trying to prevent liquefaction, you want to look at preventing the impact of liquefaction on your tunnel. And I hope that helps with answering the question. Should I move on to the next question, by the way? I saw in the list here.
Yeah,
Would you
there
like?
is next
Okay,
question.
so I will read it. I think there are two related questions, 1 and 2. What's the best software for seismic analysis of tunnels, surface structure? And then there is a specific software that is mentioned. I'll go through that next. It's always you have to find the right tool for the right problem. For the problems, the class of problems that I demonstrated, which is the underground buried reservoir, as well as tall bending underground structures, also for subway stations. These are very complex structures. We have looked at many different software platforms. In fact, at the time when we were doing the work for the buried reservoirs, for example, we were looking at a software, a different commercial software, but it actually couldn't perform as well as the other one we use, which is LS-DYNA. That's the one I have mentioned to you. It's an explicit code. What we found is that it is highly optimized, runs very fast, and runs in parallel. So it worked very well. And we used it for a real project as well as for our research. Now, there is a related question about the software platform. It mentions Abacus, Plaxis, OpenSeas. I have used all of them. It says, and other open source codes. I should mention among these three, Abacus and Plaxis are commercial codes. OpenSeas is an open source code. Okay. Now, I can talk to you directly about OpenSeas. We did try to solve some of these problems with OpenSeas. Unfortunately, OpenSeas didn't have sufficient parallelization. It also was very slow. It's more implicit, I think, that it could not solve the problem. Like, take one of the analyses that I showed you, which I can solve in an hour in LS-DYNA. It took me about a week to run it in OpenSeas at the time. And so therefore we shifted completely to LS-DYNA. Now, you mentioned Plaxis and Abacus. Okay, now let's talk about Plaxis. Now, Plaxis has many advantages. We're very familiar with it as geotechnical engineers. The fidelity of the structural modeling is still low compared to what I can represent in other platforms like LS-DYNA, like Abacus. So for a certain class of problems, like the problems I showed you where I was comparing the pseudostatic versus seismic analyses, These were all done with Plaxis, by the way. So for that class of problem, it was useful. Now, if I have to deal with things whereby I have a complexity of, say, shear walls within its station, or even building tunnel interaction, we didn't find that to be, it wasn't the right tool for that particular problem. So I wanted you to, so as I said, I've used all of these tools myself. I have firsthand experience, and that's where we ended up settling on that particular platform, just simply because of its great efficiency. We also developed our own material constitutive model there, that actually we make available to anybody who wants it, but you have to have the license for LS-DYNA. That also will allow you to model liquefaction, for example, as well. So we found it to be incredibly useful for us. Now, it says the last question in here was, what is your suggestion?
Before you move to that next one, can I add one more thing? Just as a caution, just a caution, before we move to more advanced numerical methods, I would encourage everyone to do some hand calculations or some empirical procedures to kind of understand where you might see problems and issues. Because if you move directly to advanced numerical work, you may be very confident in the very wrong answer.
Absolutely. I cannot agree more with you, Conrad. So thank you for highlighting this. Absolutely. Absolutely. It's critical. And that's why we show in the presentation, you start with the simplified solutions, and then you move to those. And by the way, if you develop a numerical model with these advanced tools that replicates a solution, a problem that is closed form, and you don't get the same answer, you need to be very careful, because you need to make sure that you're able to reproduce the known solutions before you go beyond that. So I'll cover the very last point here. What is your suggestion on boundary condition modeling in numerical analysis of tunnels? I think we can spend days talking about these. It's a very problem specific. You need to pay a particular attention to it. You have a variety of boundary conditions. You have the large free field boundary condition that you have to deal with and make sure that you are truly farther away from an area where the particular interaction you are interested in, so you're not seeing boundary effects. And you want to make sure that the waves are not bouncing back and being trapped in your model. So there are many, many issues. This is the kind of things that, the cautionary things that Conrad is highlighting there. So I hope that's helpful. And I think, let's see, I will stop at this point.
Yeah, sure. There's one more question also. Anyone?
Sure. Let me just quickly read it. So let me read it loud now for everyone. How do current seismic design approaches account for soil structure, interaction, and ground deformation effects for shallow urban tunnels, particularly when liquefaction or fault-induced ground movements are expected? So let's take it one by one. So if in going back to my presentation, in that you would have to go through a stepwise process as you start looking at issues of soil structure interaction, and based on an initial evaluation, you realize, okay, I do need to capture that full interaction. That's where you would need to represent that via a numerical analysis tool, and we just discussed the different numerical analysis tools. Now, there are two things that are mentioned. One is liquefaction, and the other one is fault-induced displacement. So one of the things we have done as part of our work, because we needed to look at issues of interaction of underground structures with potentially liquefiable soils, there are material models that are designed to capture that, and so you can represent it. However, let me caution you, is that eventually with liquefaction, you are going to move from a continuum behavior to a discontinuum behavior, especially when you have this uplift. The analyses will give you an idea about that that when you're going to cross into that threshold, but they're not necessarily reliable to tell you what will happen post-liquefaction. In fact, all continuum tools, regardless of analysis platform, post-continuum behavior, you just simply cannot represent it, okay, with these tools. Now, fault displacement, that's something we deal with all the time. We nowadays do represent it, and it really depends on what are you looking at in terms of the fault displacement. Is it a knife edge displacement, or is it a zone displacement? And these, we do represent them because you can have an interface where you know the fault is, and you allow the soil masses to displace or the rock masses to displace. So.
Yeah. Rahul Sharma has raised the hand. Could you please unmute?
Okay.
Thank you for giving this opportunity. Dr. Youssef, it's really pleasure to listen you, just like as we read your articles, many on the seismic vulnerability assessment. So I just had one question regarding pushover analysis. So are you doing, can you guide something that in tunnels, how we do pushover analysis, or what will be the good literatures available nowadays in this regard?
So we have to kind of look at the origins of the concept of a pushover analysis. Okay, the pushover analysis concept it started in structural engineering, where you have, say, a bridge or a building, and you are doing that kind of pushover analysis. Now, for underground structures, the equivalent to that would be something like a racking type of displacement, right? And you're looking at those racking displacements. So under conditions where you have low strains in the soil or weak ground motions, a pseudostatic racking kind of deformation would work. However, in situations where you have very strong ground motion, high soil nonlinearity, softer soils, and also stratification, like a change in the soil strata over the tunnel cross-section, then a dynamic analysis is more suitable to capture the nuances of the response. Similar to, if you think about for structural analysis, pushover is one step, but actually we are now way beyond that, and we do a lot of full dynamic analysis of our structure. We need to do the same thing for our underground structures. So we have those procedures, they're available to us, they're a good first step to kind of get our arms around the problem. But I'm finding nowadays, especially in highly seismic areas, that we need to go beyond it. Why? Because the requirements of the performance of these structures are going further and further, becoming higher. Meaning, say I have a metro system, the demand is that I need those tunnels to be operational within a very short period of time after an earthquake, because that's a good way for people to move around. The stations themselves, these are very expensive structures to build, and so I want them to I want to make sure that they're going to not just survive and I am able to safely evacuate people, but I want them to be operational, for example, even after severe earthquakes. That's what we're designing many of these structures for. So this elevated demand requires sharpening our pencils, and the equivalent of sharpening our pencil is using more advanced analysis tools.
Okay, thank you. So preferably it's just a preliminary kind of examination for stratified layers. But if I want in a larger context, it will be better to go in a dynamic analysis.
That is correct. That is correct. And I mean, and also the way I say it, you don't go for any project. You start with your more important infrastructure projects, because they have also the budgets, the resources, the engineering teams to do these things. And then you bring a panel of experts that can help you also come along and sort of train folks locally so that they can approach these problems well. And I've seen that being successful in many teams and many projects.
Thank you. Thank you. Thank you so much.
Thank you, Professor. I have one last question. This is from my side only. considering seismic design for tunnels, what are the limitations of using simplified analytical methods compared to full 3D numerical modeling, particularly when addressing longitudinal seismic effect of long tunnels?
Sorry, I didn't catch the last one, particularly when addressing.
Particularly when addressing longitudinal seismic effect in long tunnels.
Okay. Now, so if I'll reference a little bit my presentation. If I have a circular tunnel that goes for a long distance, and the ground conditions are fairly similar, I might find that using simplified approaches, including 2D finite element analysis, pseudostatic, or even dynamic, these are very, very, very accessible to be sufficient. However, where I have my tunnels go into a station, or I have very tall buildings, really tall buildings, and we found that if you go anything above 10, 12 stories, this is something you may have to start to consider. Then you would want to deal with more advanced conditions. So anytime where you see that 2D condition not being properly representative of real world condition, that's where you would go for that. And the structure has to be, of course, important and relevant. So for these, you would go. You don't go for everything, for absolutely everything using these advanced tools. No, there is a stepwise approach. There's a screening approach that you can go through and say, okay, for these, it's enough. For these specific conditions, you need that. We were surprised, for example, when we were dealing with these special structures, these shallow buried reservoirs, is that the 2D condition was highly unconservative because it missed a failure mode, which was the accumulation of forces in perpendicular walls as you go towards the corner. So that's where we were unconservative in that, right? So one needs to use engineering judgment, evaluation process, bring in experienced teams together to walk through and then decide where you want to do these advanced analyses, where preliminary or the simplified analyses are suitable. Think of it as toolbox. It's a toolbox. You have different tools for different problems, and you need to pick them appropriately.
Okay, that said, yeah, do you have time to have one last question?
Oh, I actually do have a little bit of time, so please go ahead.
Yeah, this is the last question. How effective as DAIym tools such as particle flow code in capturing seismic effect in tunnels? Because the most seismic analysis focus on displacement and deformation behavior.
Right. So, if you're dealing with, let's say, tunnels in rock, and it's a jointed rock, whereby the jointing behavior is important and the tunnel is unlined, tools that can model the discrete behavior of these tunnel or rock blocks can be helpful, and we have used it actually in analysis. But in a tunnel that you are going to have it that is lined and you are going to try to keep the movement to a minimum, you may or may not need that. You can, for example, have continuum model, but using a rock joint model within a continuum model. Now, I think there was a mention of a PFC, particle flow code. So I am very familiar with that code, but also we have our own code with discrete elements, polyhedral particles. Computationally, this is very expensive to run, to actually represent if especially you're dealing with soil. And depending on what you have in terms of representation, so particle flow PFC code, if I'm correct, it's spheres and ellipsoids. then you're really not representing particle shapes, and you will need billions of particles to represent that. So I am not sure why I would want to use it at such a code for the class of problems that I am familiar with. I'm not saying there is no space for it, but in general, I am not sure that this would be what you want to use. Now, separately, we are working on greatly advancing and speeding up discrete element models. We found some very interesting things. I'm going to keep it at that point until we get our papers written up. So there is a lot of space to advance, but I would love to hear what is the specific use case that is being viewed here, because as I said, generally I have not seen them. I've seen them, and I worked with Professor Jamshid Gabousi at Illinois, whereby these were used actually to do a dynamic analysis, but I can see the application to be quite limited. I hope this answers the question.
Thank you, Professor, for all the answers and your time. Thank you all the delegates and all the participants for your active engagement and your thoughtful questions. If anyone having question, please come back to us. We will like to share it with the speakers, and we'll have the solution. For those who couldn't attend or wish to revisit the discussion, our previous webinars are available on YouTube channel, and this session will be uploaded shortly after necessary permissions. If you are not yet a member and would like to join, please reach out to us on LinkedIn, on Gmail, or on our website. Thank you once again for joining us today. We look forward to seeing you in our future sessions.